Okay, so in class we had a chance to look at how exponential growth is this very powerful growth, how it might take a while to build up, but once it has some steam, it just takes off. And we saw that happen with our lily pad problem. We saw that happen with money and the way money grew. We also saw how that worked with folding paper. And a surprisingly few number of folds got us from the floor to the ceiling. But now I want to take a look at, okay, how do we graph this crazy growth? And we're in luck because we already know how to graph any type of function thanks to this world-renowned BIRATH technique. So on your notes, you can look on the back page of your notes, and the 4 graphs we work on through this video are back there. Follow along, pause the video as you need to, and do some thinking on your own. So the first thing we do anytime we're graphing any function is we find the new origin. Now remember, sometimes these functions are shifted left or right, or they're shifted up or down. And the way we can tell that they're shifted is when we add or subtract numbers inside the function or outside the function. Anytime you add or subtract, that means that the graph is sliding or translating left, right, or up or down. But that's not happening here. As a matter of fact, we won't deal with that until the last example. So the origin for this particular graph is going to stay the origin. It's going to stay at 0, 0. It seems that I'm not very good at writing with my mouse. Okay, so that's where all of my movements are going to take place. They're going to take place from 0, 0. And I just said movements, which means you now know what the second step is. We strip down the parent function. We take away anything that we're adding, subtracting, any extra scalars that we're multiplying by, and we make a table of movements from that origin that we just found. So I went ahead, I realized that this is already stripped down, that there's nothing to take away from this. There's no adding, subtracting, there's no multiplying. It's just y equals 2 to the x. And I made my table of movements. Well, I kind of made my table of movements. I like the starting lineup, -2, -1, 0, 1, and 2. And then I plugged in these values for x. So when x is -2, 2 to the -2 is 1/4. When x is -1, 2 to the -1 is 1/2. Remember again, those negative exponents, those flip the numbers. They're the reciprocal. They flip things. 2 to the 0, oh, be careful. 2 to the 0 is 1. 2 to the 1st is 2. 2 squared, 4. And it looks like we have so much space here. I added some numbers to my starting lineup. You know, with all this space on this graph, I tried 3. 2 cubed, don't say 6. It's 2 times 2 times 2. It's 8. 2 to the 4th, 16. And once I have this table of movements, I can go to my origin, wherever that origin is, and it just so happens it didn't move. And from the origin, I can plot these movements. I'm going to go left 2 and up 1/4. So left 2 and up 1/4. Oh, that's just a little bit right there. I'm going to go left 1 and up 1/2. From the origin, left 1 and up 1/2. I'm going to go over 0, up 1. Right there on the y-axis. Right 1, up 2. Right 2, up 4. 1, 2, 3, 4. Right 3, up 8. And then it looks like I can go right 4 and up 9, 10, 11, 12, 13, 14, 15, 16 and get there. And if you look at that, you'll notice that it's kind of going slow. It's not really moving very fast until we start to build up some substance. And then, whoom, it takes off. Now, we do have to ask the question. This graph is, I'm going to try my best to draw this here with the mouse. Let's see how it works. This graph is, that's not bad. Oh, look at me go with the mouse. Is taking off. shooting up there. I mean, the next number is when x is 5. And when x is 5, y is 32. That's way off my computer screen. But over here to the left, you'll notice we keep getting smaller and smaller, and it begs the question, will this graph dip below the y-axis? And the answer to that is no, it can't, because you can't raise 2 to a power and make it become negative. And if the graph is getting closer to the x-axis but doesn't touch it, that can only mean one thing. And that one thing is we have an asymptote right there, passing right through our origin. So let's see how we graph some other exponential functions. So this second problem is like the first, except you'll notice my base has changed. My base is now a 3. And let's see how that base of a 3 affects this graph. So, BIRATH technique, first thing we do, find the new origin. Again, I'm looking for adding or subtracting because that's going to shift things. There is no adding or subtracting, so it looks like my origin is going to stay 0, 0. It's not going to change. The origin is my new origin. All of my movements are going to come from that 0, 0. Then we strip down the parent function and we make a table of those movements. So there's my parent function. There's my table. I use the same table as before. This time when I plug in -2 for x, remember the base is 3. So 3 squared is 9. The negative flips it. It's 1/9. From my origin, I'm going to move left 2 and up 1/9. Oh, that's a tiny bit. When x is -1, 3 to the first is 3, but a negative exponent flips it. From my origin, I move left 1, I go up 1/3. Boom. Not much. When x is 0, we get 1. That's the point. 0, 1. Move over 0, up 1. When x is 1, we get 3. Boom. When x is 2, we get 9. Notice we're growing a lot faster than we were before. When x is 3, we get we're off the graph. We are off the graph. So when I go to draw this curve, I can get this. Again, I'm drawing with my mouse here. Let's see how I do. Oh man, Mr. Breath. Now remember, this graph does not go to this next line here until it reaches a y value of 27. I'm not going to see that on this graph. So I'm not going to draw a line that goes woo like that. No, that'd be terrible. No. What I'm going to do is I'm going to keep this graph going up. It's slowly moving to the right, but it should touch that line until way up here at 27. And then on this side, I'm going to come down. I'm going to hug the x at, well, okay. Hug the x, oh geez. Hug that x-axis as close as I can. And what happens? Asymptote. So this is exponential. It flies up. But if we compare this curve to this curve that we drew here in the previous page, this one here, let me come over and I'll sketch that. This purple curve, y equals 2 to the x, it also passed through this point, but when x was 1, y was 2, not 3. When x was 2, y was 1, 2, 3, 4, not 9. When x was 3, we were up to 4, 5, 6, 7, 8. So this graph just was a much, well, that's not very good, a much slower graph, y equals 2 to the x. It still is pretty incredible growth, but you'll notice the bigger base, the faster the growth. And of course, all of this graphing, and by the way, I hope you're pausing and you're keeping up on your graphs in your notes. All this graphing begs the question, what if the base is a fraction? What if the base is smaller than 1? It's not negative. It can't be negative. We talked about that in class several times. But what if it's like a fraction? Well, the BIRATH technique has us covered. Find the new origin. Again, I'm not adding or subtracting a thing, so it's still going to stay at 0, 0. I strip the parent function down and make a table of movements. Again, y equals 1/2 to the x. So here's my table. There's my starting lineup. I start plotting some points. I put in -2. Now, 1 squared is 1. 2 squared is 4. So if this was 1/2 squared, it'd be 1/4. But the negative flips it, which gives us 4. So from my new origin, I'm going to go left 2 and up 1, 2, 3, 4, and I'm right there. When x is -1, 1/2 to the first power is a half, but the negative flips it. So -1, I go up 2. Anything to the 0 power is 1. Well, any non-zero to the 0 power. A half to the first is just a half, so I go over 1 and up a half. 1/2 squared would be a 4th. And then 1/2 cubed would be an 8th. You see what's happening here? This graph is good. And I mean, I could keep adding numbers down here, like 4, 5, 6, but I think I want to add them up here. I think I want to look at -3 and -4. 1 cubed is 1. 2 cubed is 8. So this is 1/8, but the negative flips it to 8. So from my origin, if I move left 3, I'm going to go up 8. When I take a half to the -4, that becomes 16. 9, 10, 11, 12, 13, 14, 15, 16. And you can see we have that exponential, well, this is not, I missed it. This is not exponential growth. It's the opposite of growth. Instead of growing quickly, it's decaying quickly. This is what's known as exponential decay, where my function, you can see it starts out really big, but very quickly it gets smaller and smaller and smaller. By the way, never reaching 0, never reaching a negative, so we still have an asymptote, but it just keeps getting smaller and smaller. Well, for our last graph, let's take a look at something that has some extra stuff in it. So our last graph of the day is this. And the BIRATH technique has us covered. The very first thing we always do is find the new origin. How do we find the new origin? Well, we look for adding and subtracting, and there's a lot of that going on here. The x value, we have a trick. Our trick is we set whatever's inside the function, and what's inside this function is this x plus 3. So that's the function itself. I take that and I set it equal to 0 and I solve. And when I solve that, I get x equals -3. And so for my origin, I know that the new x value is -3, and the new y value is whatever's happening outside the origin. And so, I'm sorry, outside the function. And so what's happening outside this function is we're dropping down 1. So I'm going to take my pencil, I'm going to go from the origin, left 3 and down 1, and that point right there, very lightly, that's going to be my new origin. All of my movements are going to come from that spot. Not the original origin, but this new origin. Speaking of movements, it's time to strip down to the parent function and make a table of those movements. So when I strip it down, the bare essence is y equals 2 to the x. We already did a table of this. We already have that table, so I just borrowed that table from the earlier problem. And from this new origin, I'm going to handle these movements. Left 2 up a 4th, left 1 up a half, over 0 up 1, over 1 up 2, over 2 up 4, over 3 up 8, over 4 up 9, 10, 11, 12, 13, 14, 15, 16. And then I take my pen, I draw as smooth of a curve as I can. Okay, that's all right. As I can. And the last thing that I need to make sure I add is my asymptote. And remember, the asymptote doesn't go through the original origin, it goes through our new origin. Well, now you have your problems. Get started on your homework.